Everyone, welcome to this second session of the workshop. So I will be chairing, and are we already starting on the time for the next speaker? I'll be quick. So we'll start the session by a presentation from Thomas Erlebach on parameterized temporal graph expression. Parameterized temporal expression problem. Please. The floor is yours.
Thank you very much for the introduction, and also thanks to the organizers for once again organizing this very nice workshop and giving me the opportunity to speak here. So this is joint work with Jacob Spooner, who unfortunately cannot be here because he's now working in industry and his employer needed him today. And some of you may have heard a previous version of this talk at SAND already, but the last part of this talk is new material, so there will still be something new. The temporal graph model that we're using is the same as in the first two talks you heard this morning, except that I'm not presenting it as edges with a label function, but as a sequence of layers, where each layer is a graph, all of which have the same vertex set, but the edge set in each layer can be different. And the underlying graph is just the union of all the layers. And if an edge is present in layer T or at time T, then we call this combination of the edge at time T a time edge. And I will draw it as an edge with the label T next to it. So there the labels show up again. And the first two talks today were all about the strict model, where a temporal path or a temporal walk is something where in every step you can use at most one edge. So for example, from left to right, this is a strict temporal walk where you use an edge at time 3, another one at time 5, one at time 6, one at time 8. And the second model, which actually I will mainly talk about in this talk, is the non-strict model, where you can use as many edges as you like in each time step. So the sequence of time steps of the edges of your walk needs to be non-decreasing, but it does not have to be strictly increasing. So this walk here has used three edges at time 2, and then another edge at time 4. And the temporal exploration problem that I've been interested for quite a number of years now is you're given a temporal graph and a start vertex S. Decide whether there's a temporal walk that starts at S at time 1 and visit all the vertices. So for this talk, we look at this decision version. Sometimes you also look at the optimization version where you want to find the fastest exploration. But now let's just assume we want to know, can that graph be explored or not? And the number of time steps that we have is what I call the lifetime, which was called the age of the graph in the previous talk. So some previous work in the strict model, temporal exploration was defined by Michail and Sperakis in 2014. And one of many results they showed was that it's NP complete to decide if a temporal graph can be explored at all. They proposed considering the model where the graph is connected in every step. So every layer is a connected graph, and you assume that the lifetime is at least n squared, where n is the number of vertices, because this guarantees that the graph can be explored. And later we showed with Hoffman and Kammer that every graph under this assumption can be explored in O of n squared steps, and that there is no O of n to the 1 minus epsilon approximation for the problem of computing the fastest exploration unless p is equal to np. And there are some other papers that show that for certain assumptions about the graph, you can explore the graph faster than quadratic number of steps. For example, if the graph is, if the underlying graph is planar or has bounded tree width, or the graph in every step has bounded degree. So in many of these cases, you can get smaller upper bounds than n squared on the number of steps you need to explore it. For the non-strict model, Jacob and I had a paper at Scirocco 2020, where we showed it's NP complete to decide if the temporal graph can be explored. If the graph has temporal diameter 2, that means you can get from any vertex to any other vertex in 2 steps. We showed you can always explore it in O of root n times log n steps, and that you cannot approximate the fastest exploration problem with ratio O of n to the 1/2 minus epsilon unless p equals np. If the diameter is 3, then we showed you may actually require theta n steps to explore it. And you cannot obviously do it in 3 times n steps. And we showed there's no n to the 1 minus epsilon approximation unless p equals np. And just some auxiliary result that we'll use several times is what's about the problem if you are at vertex v at time t and you want to get as quickly as possible to some other vertex w. So that means you want to find the foremost temporal walk to get from v at time t to some other vertex, or maybe even to all other vertices. Maybe for all other vertices, you want to know what's the fastest way to get there. So in the example above here, the fastest way to get from v to w would be to wait for 1 time step at v and then use this edge from v to w at time t plus 1. This problem can be solved in polynomial time efficiently. There's papers by Buichuan et al. And Wu et al. That look at this problem and variants of it. So for example, you can do this in O of L n squared time. And you can also do it in similar time for non-strict walks. So finding a fastest walk from one vertex to another one is an easy problem. The difficulty in temporal exploration is to decide in which order you want to visit the vertices. Once you know the order, you can quickly decide what's the fastest way of visiting the vertices in that order. The order is the difficult thing. In this talk, we are interested in the parameterized complexity. That's because deciding whether temporal exploration exists is NP complete in all the variants. So we don't expect polynomial algorithms, but we want to know, are there parameterized algorithms for temporal exploration or variants of it? FPT was already defined, so if a problem with size n and parameter k, if you can solve it in some function of k times n to the O of 1 time, then the problem is fixed parameter tractable. And we would like to find such algorithms for deciding whether temporal exploration exists. And some parameters you might consider is the lifetime, which is an interesting parameter, especially in the non-strict case, because in the non-strict case, even if the lifetime is very short, it may still be possible to visit all vertices. And another parameter could be the maximum number of connected components you have in every layer. Because maybe one motivation for the temporal graph model is that you have a network where sometimes edges fail and that may disconnect the graph. But it's unlikely that many edges fail, and therefore the number of components you have in every layer is likely to be very small. So that could be another natural parameter to consider. And in addition to the standard temporal exploration problem, we've also looked at variants, namely, what if you want to visit k-specific vertices? So you're given a set x of k vertices, and you want to decide, can I visit all of these k vertices? That's the k-fixed text problem. Another variant is you're just given a number k, and you want to visit k different vertices. You don't care which k vertices they are. You just want to visit at least k different vertices. Can you do that? And another version is the set text problem, where you're given m vertex subsets Si, and your goal is to find a temporal walk that visits at least one vertex from each subset. So that's kind of analogous to the TSP problem with neighborhoods, where you don't have to visit every vertex of the graph, you just have to visit at least one vertex from each neighborhood. Or maybe you want to do sightseeing in Paris and you want to visit at least one park, at least one museum, and at least one restaurant. So you have 3 sets of destinations and you want to visit at least one of each set. So what are our results? So for the temporal exploration problem with parameter lifetime of the graph, in the strict case, it's kind of trivial to see that that's FPT. We can show that even in the non-strict case, where the lifetime can be very small compared to the number of vertices, that is also FPT. For the problem where you take as parameter gamma, the maximum number of connected components per layer, from previous work, it's already clear, even for gamma equal 1, that's NP complete, so there's no chance for an FPT algorithm. For the non-strict model, we can show that if gamma is 1, then the problem is trivial. If gamma is 2, we can still solve it in polynomial time. But for gamma 3 or larger, we don't know yet. So it could be FPT, it could be in XP, We don't know yet. For the k-fixed and k-arbitrary text problem, we can show that it's FPT in the strict and the non-strict case. For the set text problem with parameter lifetime, so for the k-fixed and k-arbitrary, so k is the parameter. For the set text problem with parameter L, we can show it's W2 hard in both strict and non-strict settings. And in the rest of the talk, I will briefly talk about these results for k-fixed and k-arbitrary text for the strict case, and then mainly about text with parameter L and gamma for the non-strict case. So let's first talk about strict temporal exploration. K-fixed text, so we want to visit k-fixed vertices. A trivial algorithm would be to simply try all k factorial orders in which you might visit these k vertices, and for each of them, check whether you can visit them in this order by going as quickly as possible from the first to the second to the third vertex, and so on. We can do a little bit better than that by using a dynamic programming similar to the classical ICALP algorithm for the TSP problem. So we can get this k factorial factor down to 2 to the k times k. For the k arbitrary text problem, where you just want to visit any k vertices, a trivial algorithm would say in n to the k time, you enumerate all possible sequences of k vertices that you might visit. And then for each of these sequences, you check in n squared L time whether you can visit them in that order. That would not be FPT. We can use color coding, the classical FPT technique by Alon, Juster, and Zwick, combined with dynamic programming to get FPT algorithms. So you basically randomly color the vertices with k colors, and then use dynamic programming to check, can you visit k vertices of different color within the lifetime of the graph. And as always with color coding, you get randomized FPT algorithms that have an error probability of epsilon, but you can de-randomize it using k-perfect families of hash functions, and then you get a deterministic FPT algorithm. Okay, that's all I want to say about the strict exploration. Now let's move to the non-strict exploration problem. In the non-strict model, the problem is actually quite different. And in every layer, the only thing that matters is what are the connected components of that layer. Because you're allowed to use as many edges as you like in each layer. So whenever in some layer you are currently in a connected component, you can always visit all vertices of that connected component and then go to the vertex in that component where you want to wait until the next layer starts. So everything that matters is what are the connected components in each layer. In particular, in step 1, you will visit all the vertices in the connected component of S, and then you'll decide in which vertex do you wait until the second layer starts, and so on. And so you basically, a temporal exploration or a temporal walk is specified by saying which component do you want to be in each layer, and the only condition is that the layer in step I and the component you are in step I and the component you are in step I plus 1 must share a vertex, because via that vertex you can get from one layer to the next. And in this graph up here, our temporal exploration could choose these red components. Every vertex of the graph is in at least one of these components, so we visit every vertex, and the red arrows indicate a possible way of doing that. Okay, that's the non-strict temporal exploration problem. Now let's assume that the parameter is the lifetime. So we're given a graph with lifetime L and want to decide, is it possible to visit all vertices of that graph within these L layers? We get an FPT algorithm for this problem by using the bounded search tree technique. And the idea is to guess, or let's start by saying we want to guess what is the largest component that the optimal tour, so that say there exists a valid exploration, let's call it opt. What's the largest component that opt visits in any of these L steps? Because opt visits all n vertices in L steps, in at least one of the steps, it must visit a component that contains at least n over L vertices. Okay, by the pigeonhole principle. How many candidates for that component can there be? So in each of the L steps, there can be at most L components that each have at least n over L vertices. So in total, there are at most L squared possible choices for this largest component that opt might visit. So we can guess which of them by having basically L squared branches at the root of our bounded search tree. And imagine that you've already guessed I components and there are still U unvisited vertices. Then you know the optimal tour visits these U unvisited vertices in L minus I steps. So it must visit a component that has at least U divided by L minus I vertices in one of these steps. And again, in each of these L minus I steps, there can be at most L minus I components, each of which has at least U over L minus I unvisited vertices. So we have at most L minus I squared choices for the next largest component visited by opt. And combining this, you get an FPT algorithm that solves non-strict text in running time L times L factorial squared times n. So this is an FPT algorithm in parameter L. Let me illustrate this algorithm. So here we have a temporal graph with 6 layers. So first we would guess what is a component that contains at least n over 6 vertices. Let's say this is a candidate for such a component. Let's assume we guess that correctly. Now in the remaining 5 steps, we're looking at a component that contains at least 1/5 of the unvisited vertices. Let's say this is one that visits 3 unvisited vertices. Now we look for a component that visits at least 1/4 of the remaining unvisited vertices. Let's say this one. Now for a component that visits at least 1/3 of the remaining unvisited vertices, say this one. And now these 4 components together visit all vertices. Now we only need to check, is there a temporal exploration that goes through these 4 components? And that's not difficult to do. And here it's like this. So initially in the component of S, we would go to here, then visit this component, go to this component, visit this, and so on. So that's how the algorithm works. And that search tree would basically at the root have L squared choices for the largest component visited by opt, L minus 1 squared choices for the possible next largest component, L minus 2 squared choices for the next largest, and so on. So this search tree would have depth L. The number of nodes in that search tree would be L factorial squared, and we would spend NL time per node. So the total running time is L times L factorial squared. That's the FPT algorithm for parameter L. And now the latest results. So if you have gamma connected components per layer, if gamma equals 1, that means every time step is just a connected graph. And then it's trivial because even in the first time step from S, you can already visit all vertices. So it's trivially explorable. Let's look at gamma equal 2. If 2 consecutive layers have the same connected components, then we can just combine them into 1 layer because there's nothing we can do in 2 such layers. We can assume every 2 consecutive layers have different connected components. Also, if there's some layer where you have only 1 connected component, then obviously you just wait until that layer and then visit everything, and the answer is yes. So let's assume every layer has exactly 2 connected components. And then a crucial point is how can the connection from the transition from layer I to layer I plus 1 be? And there are only 2 types. So I call it a free transition. If from each of the components of layer I, you can get to each of the components of layer I plus 1. So every component of layer I has 1 vertex at least from each component of layer I plus 1. You can freely decide which layer you want to be in layer I plus 1, no matter in which component you were in layer I. If that's not possible, I call it a restricted transition. For example, here, if you're in the green component, which has vertices D and E in layer I, you can only be in the green component again in layer I plus 1, which now has vertices C, D, and E in it. And if you think about it, this can only happen if from the 2 components in layer I, one of them grows and the other one shrinks. And then if you are in the growing component, you can only stay in that component. You cannot get into the shrinking component. But from the shrinking component, you can get into both components in the next layer. So those are the only two types of transitions that are possible in a non-strict temporal graph with two components per layer. And now let's have 3 observations. So if we have such a restricted transition from layer I to I+1, and in layer I we are in the shrinking component, then we can explore everything. Because if in layer I we are in the shrinking component, that means we explore that whole component, then we can move from the shrinking component into the other component in layer I+1 and visit everything there. So in these 2 steps, we visit everything. Because the shrinking component loses one vertex, that vertex must go into the growing component, so it's possible to make that transition. Okay. Second observation that follows from that, if you have a free transition followed by a restricted transition, then you can explore the whole graph. Because in the free transition, you can go into the component that will be the shrinking component in the restricted transition. And then, as we've seen in the previous observation, in this restricted transition, we can explore everything. So if free followed by restricted, we can explore everything. Observation 3, if you have log base 2 of n consecutive free transitions, then you can also explore everything. Why is that? Because if we have free transitions, we can always choose freely which of the 2 components in the next layer we want to be in. And this means we can always choose the component that has at least half of the unvisited vertices in it. That means in every step, we visit at least half of the remaining unvisited vertices. The number of unvisited vertices reduces by a factor of at least 2 in every step. That means of the log n steps, we've visited everything. And yeah, and also remember, or also a remark, kind of if you have log n consecutive layers, you can enumerate all possible walks through these log n layers in 2 to the power of log n time, because you have kind of 2 choices in every layer. So there are only n possibilities for a temporal walk through log n layers. So how can we combine this into a polynomial algorithm for gamma equal 2 now? If a restricted transition follows a free transition, the answer is yes, the graph can be explored. Otherwise, there can be a sequence of restricted transitions followed by a sequence of free transitions. If in this sequence of restricted transitions, S is always in the growing component, then there's no decision to be made. We just stay in that growing component. If S is ever in the shrinking component, the answer is yes, we can complete the exploration. If we have these growing components and then free transitions, then we only need to try all possible temporal explorations for up to log n steps of these free transitions. There are only n possible choices. We can enumerate them and check whether one of them explores all the remaining unvisited vertices. So this gives us an algorithm in running times O of nl plus n squared log n for non-strict text. And because I should finish soon, the WT hardness result for set text is, or simple reductions from set cover or hitting set work both in the non-strict and the strict model. In the strict model, this is a W2 hard, even if the graph is a complete graph in every step. So in conclusion, so these were our results. I think the most interesting ones are the ones I've spent most time on. So the FPT algorithm for non-strict temporal exploration with parameter lifetime, and the polynomial algorithm for 2 components per step for non-strict exploration. The obvious open problem is non-strict temporal exploration with parameter gamma in XP? That means, is there a polynomial time algorithm for every fixed gamma? Or is it even FPT with parameter gamma? At the moment, even for gamma equal 3, I do not yet know whether it's polynomial time solvable or not. So the complexity for gamma equal 3 is still open. My guess would be that it's probably in XP. So I think there could be a polynomial algorithm for every constant gamma. Whether it's in FP or not, I don't have a feeling yet. So that's the end of my talk. Thank you very much for listening. I'll be happy to answer any questions.
Thanks for the talk. Do you have any question? We have one in the room.
I don't think they can hear you.
Okay, so do you hear us now?
Yes, I hear you now.
Okay. Yeah, so you can either join or we have a question from the room, but some technical issue with the microphone. Or you can just take the question and repeat the way. People can see.
So hi. So first of all, thank you for the nice talk. I was wondering that whether in the optimization case, so when you want to like reduce the time you need to explore the whole graph, and you have the starting time variable, so you not start in a fixed time, is there anything that can be done smarter than just repeating the FPT algorithm for every pair of start and end time step? Or is this the best known so far?
I've not thought about this, so definitely you could try all possibilities for start and end time and use the FPT algorithm to check whether that has a solution. But if you want to do it faster than that, I'm not sure. I mean, at least, I mean, I think if you do the start time, just enumerating all possible start times, and for every start time, I think with an FPT algorithm, you should be able to find the fastest exploration for that start time. So I don't think you have to enumerate both start and end time. Just trying all possible start times should be enough. But whether you can avoid enumerating all start times, I'm not sure.
Because like at the moment, like this would only work if like you really have the lifetime explicitly given. But if you consider like more compact representations of temporal graph, then you could no longer do that. Kind of the background of the question.
But yeah, also the FPT algorithm, we have basically the running time is proportional to the lifetime. So if you had a compact representation where the input size is much smaller than the lifetime, then yeah, then I'm not sure, because the algorithm has the lifetime as a factor, so it would not. Yeah, it depends on what parameter you consider, but the problem becomes much more difficult if you have compact representations that are smaller than the lifetime.
Okay, thank you.
Do we have another maybe quick question before we move on? If not, then I do have one. So in the FPT algorithm is the k fixed, I think. You had an algorithm in 2 to the k times k. Do you know if it's kind of optimal under AATG or other commonly used hypotheses?
We have not looked at this, so we have not. I do not know whether it's optimal, assuming ETH. No, I don't know.
Okay. Okay, then we can thanks again, speaker.